A hinged structure consists of rhombi with side lengths L, 2L, and 3L. Point A3 is moving at a constant horizontal velocity of v0. Find the velocities of the points A1, A2, and B2 at the moment when all v angles of the structure are equal to 90 degrees. Also, find the acceleration of point B2. Alright, let's solve this. The first thing you'll probably notice is that this looks like a spring, and that's because it is. If you set it in motion, it will look like this, but it will only oscillate like this when v0 is not constant, which is of course not the case over here. This means that v0 must be small so that it can remain constant while drastic changes don't occur. When all the angles are equal to 90 degrees, a rhombus becomes a square, so we are asked to find these things at this instant. A square has many nice properties, so that will likely be useful in our endeavor. Now, we can approach this in two different ways. The first way is by modeling the problem using calculus. Because this structure scales proportionally, we can write these lengths over here as x, 2x, and 3x. We are given that A3 moves at a constant speed of v0. The length A30 is what we're interested in here. Notice that this length will equal to the sum of these three, so it equals 6s. Now, here comes the important step. X is clearly a function of time. It varies as the spring moves. Precisely speaking, since O is fixed and A3 has a constant rightward velocity of v0, the rate of change of this entire length is v0, i.e., the derivative of 6s with respect to time equals v0. So the rate of change of x is v0 by 6. This was the key step. From here, we can easily get that the speeds of the points A1 and A2 are v0 by 6 and v0 by 2 respectively. Now let's deal with B2. It's a little different since it's above and not on the quote-unquote principal axis, I guess you'd call it. The horizontal distance between O and B2 is 2x, so at least we know that the horizontal component of B2's speed will be v0 by 3. Getting the vertical component will be a little trickier though. First of all, let this height of B2 at this instant be y. Then x squared plus y squared is equal to 4l squared, and this is just a constant. So if we differentiate both sides using the chain rule, we can easily see that 2x dx by dt plus 2y dy by dt equals 0, i.e., the rate of change of y equals minus x by y times dx by dt. Therefore, when all the angles of the structure are equal to 90 degrees, i.e. each rhombus becomes a square, y dot will equal to minus v0 by 6, where the minus sign denotes that it's downwards. All in all, the magnitude of B2's velocity will be equal to root 5 by 6 v0. To find B2's acceleration, we first note that x double dot is clearly 0, since x dot is v0 and v0 is a constant, so if we differentiate both sides, x double dot is a 0. So we just need y double dot. This is actually easier than we think. If we just take this equation and again differentiate both sides, we'll use the quotient rule like this, then we can clearly find y double dot. At the square transition state, y double dot will equal this, because x equals y equals L root 2. A little bit of simplification and we get that the acceleration of B2 will be v0 squared root 2 by 36L downwards. Now let's look at an alternate solution. In this second way, we utilize the same procedure to show that these velocities are v0 by 6 and v0 by 2. However, we find the vertical velocity of B2 in a different manner. This hinged structure is a rigid body, meaning the distance between any 2 points is fixed throughout the motion. But this also means that the projection of velocities of both points on the line connecting them are equal. This is sometimes called as the rigid body constraint. So, if we invoke the rigid body constraint in the pairs of points B2 and A2 and B2 and A1 at the square transition instant, we see that this component of B2's velocity along here must be V0 by 2 root 2, and the one along here must be V0 by 6 root 2. These are perpendicular components, so the speed of B2 must be their exact resultant, which equals this, which is the same result we got from the calculus method. In fact, we don't even need to stop here. If we go in the reference frame of point A2, i.e. the frame which moves towards the right at a speed of V0 by 2, then if we apply the rigid body constraint yet again, we can say that B2 must move in a circular manner with respect to A2, because its distance from A2 is constant, which is just the definition of a circle. Therefore, its acceleration must be due to the centripetal and tangential forces. The centripetal acceleration is given by v squared by r, i.e. v0 squared by 36L. We also know that the net acceleration of B2 points downwards. So the tangential component must balance out the centripetal one, so it must be also equal to v0 squared by 36L. All in all, leading to a net acceleration of v0 squared root 2 by 36L downwards, which is the same result we got by the calculus method. If you enjoyed this video, make sure to leave a like and subscribe if you want more stuff like this. This is a new series on my YouTube channel which I'm calling Physics for Olympians, where I cover Olympiad level problems from every chapter of physics. By chapter, I mean a topic which I consider to be an individual discipline of the subject. The sources for every problem discussed will be in the description of its respective video, of course. Happy learning, and goodbye!